All right. Hello, everybody. Today I'm going to be talking about supercapacitors in race cars. So, first off, what is a supercapacitor? A supercapacitor is a energy storage device. You can think of them as a high energy capacitor, but they have a lower voltage limit. So usually the highest voltage limit you'll see for a supercapacitor is about 2.5 to 3 volts. And the ones you'll really normally find range anywhere from 1 to 3 volts, like if you were looking on Amazon or any store that sells, electric hardware. Um, they're kind of like a supercapacitor battery hybrid. Like a capacitor, there are two separated plates. As we can see down here, um, these plates kind of act like electricity sponges. And although capacitors can soak up a pretty good amount of electricity, super capacitors soak up a lot more. In a regular capacitor, these two plates are separated by a dielectric. And then when the capacitor is charged, the negative and positive charges form on their own separated plates, which creates an electric field, as we can see down here. In a supercapacitor, there is no dielectric. Instead, there is a very thin insulator, as we can see right here. The plates on the side are soaked in electrolyte, not Gatorade. Um, but basically, this means when the plates get charged up, the molecules form a double layer, as we can see here. They form one row of negative and one row of positive that can be switched depending on which side it's on. And basically, all these two rodents mean is that the bigger the surface area of these plates, the higher your capacitance of your supercapacitor will be. Now on to the fun part. How are supercapacitors used in race cars? So, the main series that uses supercapacitors is IndyCar, and today I will be focusing mostly on them. Indy cars have 20 supercapacitors, and they are paired with a MGU, which is an electric motor. We can see the supercapacitors down here in this picture, and the MGU will be just below it. The MGU's job is to harvest energy through regenerative braking, and then deploy said energy later on. I know someone else touched on regenerative braking, but as a refresher, all it really is where the motor harvests energy that would previously be lost under deceleration, and it takes that energy and sends it to the supercaps and stores it there. That energy then waits in the supercapacitors until the driver decides he needs the extra horsepower. When he wants the extra power, he can push the it's called push to pass button. It's up here. It's just a little button on the steering wheel. And that sends the energy back to the MGU from the supercapacitors, giving the car more overall horsepower. The other components that work hand in hand with the supercapacitors are the DC voltage converter. So this DC to DC converter is really important because the MGU, when it harvests the energy, that energy can be at 40 volts, 50 volts, 60 volts. But if it's sensitive to the DC to DC converter, it can be converted into 12 volts, which is what the system is rated to run at. And then there's also the ECU. The ECU is kind of the brains of the operation. Without it, none of this would be able to run. It controls everything, makes sure everything's working properly. And it's also something the mechanics can edit, fiddle with if something's not working correctly. And they fit all of these components inside the bell housing, as we can see right here, which is great for just saving space and keeping all this weight in one place, which is good for the overall balance of the car. IndyCar was not the first to use regenerative braking, and MGUs in a high performance racing series. Formula One has been doing it for over a decade now. But what's the difference? Well, Formula One uses batteries. So why does IndyCar use supercapacitors and not a battery? Well, starting off, supercapacitors have basically an unlimited charge and discharge life. Um, Batteries, as we know, you got to replace your car battery. Batteries will wear out. Supercapacitors, they're they'll last almost forever. The very nature of racing promotes the use of supercapacitors. In a racing car, there's a lot of on and off the throttle, accelerating and decelerating, and using a battery to store that recovered energy. It's almost for the most part too much space. And supercapacitor, since it deploys the energy very quickly and can harvest it very quickly, it's good for the short bursts you need of extra horsepower and the big braking zones where you can harvest a lot of energy. We can actually see this in the graph here as we see the supercapacitor provides a short burst of energy, and the voltage drops linearly as it discharges. This seems to be okay for racing, as the quick discharge of all of its power allows you to get full power deployed pretty quickly. We can see the battery discharges slowly, providing energy over a long period of time. And the battery voltage remains constant as it discharges for almost the entire time it's being discharged, which can be good, but in short deployment, it's you're not getting the full power immediately like you do with the supercapacitor. So it can be good in other racing series, but as it's used in IndyCar, the way it's used, supercapacitors seem to fit better. So now I'm going to show you guys a supercapacitor regenerative braking model that I built specifically for this project. And it just showcases how supercapacitors are used in any car in a rudimentary way. So this is my regenerative braking supercapacitor model. Just a quick rundown of what everything is here. These are the supercapacitors right here. If I show you like this, you can see each one of these is an individual supercapacitor, and these boards on top just ensure that they are in parallel, so the voltage rating and the capacitance can be added up with between each supercapacitor. Um, there is a multimeter right here that is showing you the capacitance within supercapacitors. Right now there's about 1 volt. This is a DC motor right here. And it runs into this diode right here. What the diode does is it controls direction of current. So at the moment, the diode is running it's allowing the current to run this direction, which means the whole circuit is in charging mode. And if I spin up this motor, it should charge the supercapacitors. So how I'm going to do that is I'm going to spin up the flywheel, and then I'm going to hold the motor to the flywheel, and it should take the energy from the flywheel like it would an Indy car, and uh, increase the charge within the supercapacitors. So as we can see, the flywheel being spun up by the drill, allowed the motor to charge the supercapacitors all the way up to just under 6 volts. So now put the super to discharge the supercapacitors and put that energy through the circuit into the motor, we just have to flip the diode, changing the direction of current, allowing the motor to be powered, and then spin the flywheel back up just like it would in an Indy car, giving more horsepower. I mean, you can also see from the multimeter, you're going to see a kind of a linear drop off, just like we saw in the graph earlier. Okay, so we're about down to 3.5 volts here. I'm gonna take the motor off of the flywheel and I'm going to disconnect the circuit, leave an open circuit so no current is flowing. And for learning purposes and to show you the kind of energy that a supercapacitor can store, I'm going to charge up the supercapacitors using this power source and then run them in the circuit again, showing you guys how much power they really can make. We're already back up to 5 volts as the power source right here is charging them. So I'm going to go about up to 20, 22 volts, and then I'm going to hook it back up to the motor and have a spin of the flywheel. Okay, they're now hooked back up to the circuit, and the direction of the diode is pointing towards the motor, making it in the running position. So once I hook this back up, it should spin up pretty fast. And we attach the motor to the flywheel and we'll see how fast it spins. This is from 20 volts. Really quickly, while we still have some voltage, I'm going to add a little blue strip so you can see how fast it's rotating. It's right here. And we'll see how fast it's spinning up. You can see it's not staying on very well because we're getting good amount of juice from the supercapacitors, and you can see they are discharging literally. Voltage rating is going. So to build the model and do the demonstration, a few calculations went into deciding what spec parts I needed to buy. Um, so I'm just going to show you a bunch of formulas that were important to know if you're building your own or calculating your own data from the experiment. So voltage and current during charging and discharging were both really important. I needed to make sure the voltage rating and the current rating were high enough on the capacitors to then charge up the motor and have it run at a noticeably fast speed. Same with the charging. I wanted to be able to make sure the charging, the capacitors would charge fast enough with the motor spinning them up. Um, and the energy stored in the capacitor, I didn't have to calculate that, as there wasn't really a need for me to calculate for this, but for some other things, it's definitely important to know. Charge on capacitor during discharging and charging. Also, not something I had to calculate. I wasn't really too worried about the charge, but also something to know if you're doing any of your own experiment. Could be something you'd like to know. Capacitance formula. This was actually given to me when I bought the capacitors. It was I bought them online and it was in their data, so it's not something I had to calculate on my own. But it did give me data I needed for other calculations. Capacitance in series and capacitance in parallel were super important, even though they're like the simplest formulas on here, maybe except for capacitance formula. But they, I needed to make sure the capacitors were in parallel because if, as you can see here in series, the capacitance is rated at 500 farads, and I needed more than that, and the voltage rating was only at 2.7 volts, so I needed more there. So making sure they're in parallel, I had to buy those circuit boards that put all 12 capacitors in parallel. Here are my sources, and thank you guys for watching.